Modern enterprise audits operate at a massive scale. When a system is tasked with verifying millions of transactions, the efficiency of your code determines whether the task takes seconds or crashes the server. Consider this specific challenge. You have 10 million invoice IDs. Every ID is a duplicate pair, except for one. Somewhere in that list, there is a single unique anomaly that you need to isolate. This diagram shows the typical developer instinct. You create a hash map, a digital dictionary, to iterate through the list and keep a running tally of every ID the system encounters. The problem is the hidden hardware cost. For every unique ID the system finds, it must allocate a new block of physical RAM to store that information. On a dataset this size, relying on high-level software abstractions creates a physical bottleneck. A simple counting task quickly turns into a memory crisis. Engineers measure this efficiency through space complexity, the rate at which an algorithm's memory usage grows as the dataset gets larger. This chart shows the reality of a linear or O of n approach. At 10 million invoices, the map requires 10 million slots of RAM, eventually hitting this red out-of-memory ceiling. To solve this, we need an algorithm that scans the data in linear time but operates in O of 1 space, meaning it uses only a single, fixed variable for the entire operation, regardless of whether we process 10 items or 10 billion. Finding that solution requires us to move past high-level abstractions and look at how the processor handles data at its most basic logical level. Inside the microscopic architecture of the CPU, we find a specialized operator called bitwise XOR. It's designed for comparing binary data at high speed. This animation shows how an XOR gate works. It outputs a 0 if the two bits are the same, and a 1 only if they are different. This leads to our first rule, self-annihilation. Any number XORed against its exact duplicate results in 0. The second rule is identity. If you XOR any value against 0, it passes through the operation unchanged. Crucially, XOR is commutative. The order in which we process the numbers doesn't matter. The final mathematical result will always be the same. These rules provide a way to mathematically erase duplicates without the system ever having to remember them. To see this in action, we'll use a small demonstration array: 12, 25, 12, 41, and 25, 2 pairs and 1 unique number. This diagram shows our setup. We start with a single 32-bit integer called result, initialized to 0. As we loop through the array, the 0 collides with the first number 12. By the identity rule, the result container simply becomes 12. The sweep continues to the next number, 25. The 12 is XORed against the 25, moving the container into an intermediate binary state. When the loop eventually hits the duplicate 12 and 25 later in the array, the self-annihilation rule kicks in. The operation mathematically erases those values from the container, zeroing them out. Because the pairs destroyed each other, only the unique integer, 41, remains. We found the anomaly using only a single variable. The final implementation takes only 3 lines of code. It uses a single loop and the XOR equals operator to process the entire dataset. Compare this to the hash map approach we started with. There is no large data structure to manage and no complex memory allocation. This code can process millions of records while maintaining the same tiny memory footprint. While high-level tools are excellent for most tasks, they can sometimes hide the true efficiency of the hardware. Understanding bitwise operations gives you a way to solve massive data challenges by utilizing the fundamental logic already built into the processor.